The discoveries of the James Webb Telescope have sabotaged the case for the Big Bang. The James Webb Space Telescope has just conveyed an outright exhilarating revelation that is sending shock waves through the universe of physical science. Through a solitary stunning picture, it has annihilated well-established debates, leaving researchers shocked. The time of hypothesis is finished, as Webb's most recent catch is both outwardly dazzling and a game-changer that vows to alter our discernment of reality. What red-hot discussion among researchers has this picture conclusively finished? In what ways is the staggering picture caught by the James Webb Space Telescope rethinking how we might interpret the universe? Go along with us as we dive into why James Webb's discoveries are putting an end to debates in physical science with a breaking picture. The key issue with astronomy is that researchers can't come to an arrangement about how old the universe is or the way in which it is expanding. This unanswered peculiarity has baffled researchers across ages, driving them to direct different examinations to find answers. Cosmology is the field of research that spotlights on getting at how the universe was made, the way things are set up, and how it has changed over time, and at last, the way that it will end. This field has seen critical improvement in the beyond 100 years. The right now acknowledged cosmology model, the theory of prehistoric cosmic detonation, proposes that the universe has been growing from a very hot and thick introductory state for about 13.8 billion years. This development is estimated by the Hubble study, which shows the speed at which the universe is extending. Anyway, estimations of the Hubble consistent are not direct. Estimating the Hubble consistent can be extensively sorted into two gatherings: neighborhood estimations and early universe estimations. Neighborhood estimations include the investigation of cosmic bodies, for instance, Cepheid variable stars and type Ia cosmic explosions, to quantify the Hubble consistent. Because of their splendor, stargazers can measure how the universe's development influences the paces of these items to find their distances and consequently work out the Hubble consistent. The second bunch is the estimation of the early universe. Researchers use perceptions of the enormous microwave foundation radiation, CMB, the phosphorescence of the Big Bang, which was found during the 1960s. The CMB shows the microwave radiation of the early universe when it was simply 380,000 years of age. By estimating the small temperature and polarization varieties emanated by the CMB, cosmologists can lay out the age of the universe and its pace of extension. Yet, here's the issue: the aftereffects of these two strategies don't align. The outcomes noticed through neighborhood estimations affirm that the universe is growing quicker than what we gauge in view of CMB information. Because of these distinctions, researchers have been endeavoring to reveal the reasons behind the outcomes. In this way, further research is being directed to learn more about the secrets of the universe. As things stand, the distinction in estimations shows that there is, by the same token, new science we have hardly any insight into yet, or mistakes in one or the two ways by which we are estimating things. Because of the James Webb Space Telescope, we can see into the dim universe more clearly than at any other time. The telescope can show the slightest and most far-off elements, planets, and cosmic systems we could never have thought it was feasible to see. Because of its capabilities, researchers naturally expected that information from the JWST would help us in exactly computing the Hubble consistent. Anyway, the principal wave of information has surprisingly made matters more muddled. They have given us new insights that are not consistent with what we assumed we knew. Might this information at any point lead to another hypothesis and alter how we ponder space? Assuming this is the case, we could have to survey how we might interpret how the universe works. For example, we may find particles and forces that have never been noticed, or it could mean that dull energy and obscure factor liable for the speeding up extension of our universe should be reconsidered. Up to this point, the manners in which we think about space have evolved as we proceed to find new things. For instance, in 1965, when analysts found the astronomical microwave foundation radiation, it filled in areas of strength for the thought of the theory of prehistoric cosmic detonation. Before then, researchers felt that the universe was timeless and consequently was continually growing at a uniform rate. Yet, the new proof demonstrated that was not true. Likewise, when we found out towards the end of the 1990s that the universe was consistently extending at an accelerating rate, it further changed our understanding. We found dull energy and its impact on the universe's development. In this way, every time we learn something new, we question whether it squeezes into our ongoing system. If not, we concoct new ways to deal with comprehend the universe better. To this end, the issue we are looking in cosmology today could prompt the disclosure of the most awesome answers for the universe. While the issue is testing, it is likewise thrilling as it constrains us to foster all the more innovatively progressed apparatuses to investigate space. This cosmological issue additionally joins the logical local area from various nations, as each researcher needs to find out about the universe. Above all, it shows that science is continually changing and developing as we get more familiar with space. Alongside the Hubble strain, there is likewise a worry known as the SA strain. This is concerning the spatial conveyance of matter in the universe. This can be utilized to draw a primary image of the universe and perceive how it has developed. The stargazers allude to this peculiarity as unevenness because there are areas of room that have parts of cosmic systems firmly gathered, while other regions are inadequate. The researchers will utilize various strategies to gauge this unevenness, and one way is to check how out the light from far-off universes gets bowed by the different gravity of huge particles, for example, cosmic system bunches. This bowing, known as gravitational lensing, gives us a method for exploring where dull matter is, given that it is undetectable as it doesn't produce light. Specialists likewise utilize the inestimable microwave foundation, CMB, a radiance from the very start of the Big Bang. This light has been moving for around 13.8 billion years, bearing news from the early universe. Through CMB investigation, physicists can interpret how the universe was uneven in its introduction to the world, which ought to match the observational unevenness of the universe at the present time for a huge scope. Yet here's the get: these outcomes additionally don't adjust.